Hi, this is a course on electromagnetism, and in this lesson, we are going to discuss about your capacitance, current, resistance, EMF, and Kirchhoff's rule. In the previous lesson, we have discussed about your current, resistance, and EMF. And for this video, we're going to discuss about your resistors that are in series and parallel, and we're also going to discuss about your Kirchhoff's rule. In the previous lesson, we discussed about your resistors, how to read the color codes in your resistors, and how to find the resistance in your resistors. Resistors, just like your capacitors, can be connected in series and in parallel. And you do this because sometimes you cannot buy from the store the specific resistance that you're needing for your circuit. So what you do to solve the problem is to connect your resistors in series and in parallel in order to obtain for the specific resistance that you are requiring. Resistors are in series if they're connected one after the other, so the current is the same in all of them. So in this figure here, these are your resistors that are in series. You have three resistors, R1, R2, and R3. And as you see, they are disconnected in one line. And resistors are in series if the current can flow only in one direction, like say for example here. The equivalent resistance of a series combination is the sum of the individual resistances. That is, your R equivalence is equal to R1 plus R2 plus R3 plus so on and so forth. And for resistors that are in series, the series resistors have resistance larger than the largest value present in your circuit. On the other hand, resistors are in parallel if they are connected so that the potential difference must be the same across all of them. This is an example of resistors that are in parallel. So again, take note of this statement here. Resistors are in parallel if they are connected so that the potential difference must be the same across all of them. So in this case, if you're going to measure the voltage across your resistors R1, R2, and R3, you are expected to measure the same potential difference or the same voltage across the three resistors. And resistors are in parallel if the current coming from or entering a junction can move in different directions. Let's say, for example, for this current I here. So it can move here, it can move here, and it can also move here. As you see that these three resistors are in parallel. And the equivalent resistance of a parallel combination is given by this equation. You have your 1 over R equivalence is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus so on and so forth. And to get for the R equivalence, you just get the reciprocal of this one here, of the value of this sum, and you get the equivalent resistance for your circuit. Parallel resistors have resistance smaller than the smallest value present, and that is because of your 1 over R sum here. Resistors can be connected in combinations of series and parallel. For example, in this figure, you have your resistor R1 in series with parallel combinations of R2 and R3. So in order to simplify this one, you can first simplify the parallel combination of R2 and R3, and then after that one, you have your series connections of your R1 and the equivalent resistance of your R2 and R3. Or you may have your R1 in parallel with series combination of R2 and R3 here. So to simplify this one, you first take the equivalent resistance of your R2 and R3, which are in series, and you take the parallel combination of these resistors here with your R1. So you can combine your resistors in any way possible that you like. Let us have this example. Find the equivalent resistance of the network to the right and the current in each resistor. The source of your electromotive force or your EMF has negligible internal resistance. So in this circuit or in this network, you have three resistors. You have a 4 ohm resistor, a 6 ohm resistor, and then a 3 ohm resistor. And you have your voltage or your source of your EMF that's equal to 18 volts, no internal resistance. And for this problem, you are asked for the following. So first, you're asked of the equivalent resistance or your REQ. And then second, you're asked of the current in each resistor. So your I for your 4 ohms, I for 6 ohms, and I for your 3 ohms. Now let us solve the problem. So remember that you have this one here, and just like your capacitance or in your capacitors, what we usually do is to simplify first those networks that are more easier to simplify and that would simplify your network, something that would not make your network more complicated. So first, as you can see, this is what we can simplify first. Your two resistors that are in parallel, your 6 ohm resistor and then your 3 ohm resistor. And these resistors are in parallel. And you know that for resistors that are in parallel, your R equivalence is equal to 1 over, let's write this one as your 1 R prime. You have your 1 over 6 ohms plus 1 over 3 ohms. And to get for your R prime, just take the reciprocal of this one, okay? And your R prime is equal to 2 ohms, as you can see here. And we are able to simplify your resistors in just two resistors that are in series. Now you know that these are in series, so you just simplify that one, okay? And for resistors that are in series, you have your R equivalence that's equal to your R 4 ohms plus your R prime, okay? So your R equivalence is equal to 4 ohms plus 2 ohms, that's equal to 6 ohms. So you're left with one resistor in your network, and which has the R equivalence that's equal to 6 ohms. So this is the equivalent resistance for your 3 resistors in your network. Next, let us find for the current in each resistor. And for this one, you just always remember that for your resistors in series, okay, for your resistors in series, the current I is the same. And for your resistors in parallel, your voltage is the same. So always remember these two in dealing with your resistors that are in series and in parallel. So we need to find for your for the current in each of the three resistors. In doing that one, we first start with your equivalent resistance, okay? So this is how you always do it. You start with where you ended last time, which is just in your one equivalent resistor, which is your 6 ohms. And you have your 18 volts source of your EMF, and we can find for the current for this resistor here. From your Ohm's law, your V equals IR, your current for your 6 ohms, okay, that's equal to your voltage over your resistance, that is your 18 volts divided by 6 ohms, which is equal to 3 amperes. So that means for this equivalent resistor here, the current flowing in your circuit is equal to 3 amperes. Okay, now let us move backwards, okay, from a one equivalent resistor. If you remember, this one equivalent resistor is actually made up of two resistors that are in series. So you have your 4 ohm resistor and then your 2 ohm resistor. Okay, and remember that in series, your current I is the same. So that means for your 4 ohm resistor and for your 2 ohm resistor, the current before, which is in 3 amperes, is the same current that is flowing in your 4 ohm resistor and in your 2 ohm resistor. Thus, you are now able to find for your I 4 ohms, and that's equal to 3 amperes. Let me erase this one. So again, for your 4 ohms, you have a current of 3 amperes. Okay. And after that one, remember that this 2 ohm resistor here is actually a combination of two resistors that are in parallel. Okay. So let's go back one step up and we go back to our original network. And remember that for your resistors that are in parallel, the voltage V is the same. So let's find first for the voltage here in your 2 ohm resistor. Okay. And for that one, you just have your V equals IR. So you have your 3 amperes times 2 ohm. So that's equal to 6 volts. And you can also find for the voltage for your 4 ohms. So that's just 4 ohms times 3 amperes. So that's equal to 12 volts. And as you can see, 12 volts plus 6 volts, that's equal to 18 volts. So what happens with the voltage in your resistors that are in series is that your voltage is split into your 4 ohm resistor and then into your 2 ohm resistor. So the sum of the voltage for these resistors that are in series should be equal to the applied voltage in your network. Okay, so we're able to solve for the voltage in your 2 ohm resistor. And we said earlier that for resistors that are in parallel, the voltage V is the same. So going one step up, so you see that your 6 ohm resistor and then your 3 ohm capacitor are in parallel, which combines into your 2 ohm resistor. So that means that for your 6 ohm resistor, there is 6 volts here, and then for your 3 ohm resistor, you also have 6 volts of potential difference that can be measured for the resistor. Okay, so you have your voltage and you're asked for the current in each resistor. So for the current in your 6 ohms, okay, here, this 6 ohms here, this is equal to your voltage 6 volts divided by 6 ohms, which is equal to 1 ampere. And for your current in your 3 ohms, this resistor here, you have 6 volts divided by 3 ohms, so you have 2 amperes. Therefore, the current for your 4 ohm, your 6 ohms, and then your 3 ohms resistor are the following. You have 3 amperes, 1 ampere, and 2 amperes. So that is how you are going to solve for the current and the voltage in each resistor in your network. So as a review, what we did first was to find for the equivalent resistance, and then from the equivalent resistance, we go back to our network one step up, and then we solve step by step your voltage and the current in your resistors. In most cases, you cannot simply solve the current and the voltage in each resistor by just simply having your resistors that are in parallel and in circuit, or in parallel and in series. And sometimes your resistors are connected in a much complicated way, more complicated than just a simple series and in parallel. So in order to solve for the current and the voltage in your resistors, which are connected in a more complicated way, we can use your Kirchhoff's rule. So your Kirchhoff's rule, which is sometimes also read as your Kirchhoff's rule, named after Gustav Robert Kirchhoff, okay, has two rules. So the first rule is your junction rule, and then the second one is your loop rule. And we're going to discuss these two rules individually. But before that, let us define what a junction is. A junction is a point where three or more conductors meet. So again, a junction is a point where three or more conductors meet. So let's say, for example, here, you have this junction here. Because we have three conductors or your three wires, you have first 1, 2, and 3 that meet at a certain point. So you can also have 4 if you can add another conductor or wire here. That's still a junction. But if it's just two conductors or two wires that meet at a point, like say for example at this point here, so just have 1, 2, then you cannot call this one as a junction. So this is not a junction, this is not a junction, this is also not a junction. Of course, this one is also not a junction. This is a junction, A is a junction, and point B is also a junction. So again, a junction is a point where three or more conductors meet. On the other hand, a loop is any closed conducting path. So for example, for this case here, this loop here, since this is closed, or since this path here is closed, you call this one as a loop. This one also, this is also a loop. And this one, okay, just follow the red laser. So this one, this is also a loop. So for this network here, you have three loops. One, the bigger loop. This is 2, and then this is the third loop. So this network has 2 junctions and 3 loops. Loops start and end at the same point. For example, for this case here, let's first find for your junctions. So again, a junction is where is a point where 3 or more conductors meet. That means A, B, C, and D are junctions, while F and E are not. You have here this loop here. Again, please follow. This one here, this is a loop. Or let me draw it. So this one here, this is a loop. Okay. Above, this is a loop. Sorry. I just want to show it what the loop is that I'm referring. So this one here, this is a loop. This one here is also a loop. So that's quite dirty. Let's erase this one. Okay. Those are your loops. And another loop is this one here. This is the second loop. Okay, and this is the third loop. And this is your fourth loop. So for this network, you have 4 loops that you can find. Now let's discuss your first rule, your first Kirchhoff's rule, which is your junction rule. And again, we have a junction that is a point where 3 or more conductors meet. And by the way, why are we going to use your Kirchhoff's rule here? It's because, as you can see, these 3 resistors are not resistors that are simply in parallel. Why? Because these resistors are connected to this voltage source here. So that means these 3 resistors are not simply resistors that are in parallel because of this power supplies here. What's your Kirchhoff's first rule? So it's called your Kirchhoff's junction rule, and it states that the algebraic sum of the currents into or out of any junction is 0. Again, the algebraic sum of the currents into or out of any junction is 0. So we have seen earlier that for this network, you have 2 junctions A and B, and according to Kirchhoff's first rule, your junction rule, the algebraic sum of the currents into or out of any junction is 0. That is, all the currents coming into or going out of this junction should should sum up to 0. That is, the sum of all the currents into or out of any junction is equal to 0. Again, for your Kirchhoff's junction rule, the algebraic sum of the currents into any junction is 0. That is, the sum of all your I is equal to 0. And this follows your conservation of charge in time for steady state currents. And here, this is a part of the network that we have earlier. And consider this junction here. And let's say that you have three currents. So you have current 1, current 2, and then current 3. Current 1 is going into the junction. Current 2 is going into the junction, and then current 3 is going out of this junction. A water pipe analogy is you have this one here. You have two waters going inside, and then another water going inside, and these two waters, they combine into this water here that flows out, and the flow rate of the water leaving the pipe equals the flow rate entering it, as you know. And this is similar to your current. What we have here is, since you have these two currents here going inside, and then going outside, the current leaving the junction equals the current entering it. So that means current I1 plus current I2, that's equal to your current I3. And the convention for this one is that any current entering the junction is positive, and any current going out of the junction is negative. So this is actually, for the sum here, it's actually written as the sum of all your I, that's equal to your I1 positive plus I2 positive minus I3, because it's going outside, and that is equal to 0. Thus we have your I1 plus I2, and that's equal to I3. Again, this is just a review of your Kirchhoff's junction rule. So it states that the algebraic sum of the currents into or out of any junction is equal to 0. And we have your sign convention that for currents entering your junction, it's positive, and for currents that is going outside of your junction is negative. So for the sum of all your I for this junction here, you have your I1 plus I2 minus I3, and that's equal to 0, or you have your I1 plus I2, that's equal to I3. Next, let's discuss about your Kirchhoff's second rule, your Kirchhoff's loop rule. Okay, and your Kirchhoff's loop rule states that the algebraic sum of the potential differences in any loop must equal to 0. That is, the sum of all your voltage in any chosen loop should equal to 0. And just remember that you have um, your voltages in your resistors, and then you also have your voltage from your power supply, or your source of your potential difference, or your EMF. And here, let's say for example, in your loop 1, looking into loop 1, this bigger loop here, the biggest loop in this network, so this one here, let's start from point E. Okay, so you have this voltage here plus the voltage passing in your resistor, plus the voltage passing in resistor R2, plus the voltage passing in R4, and then back to point E. The sum of all the voltages passing across your components should equal to 0. Another example is in your loop 2. Okay, so let's start with the same point E. So you have your voltage from your EMF plus the voltage in your resistor R, or this is in your internal resistance, plus the voltage in R1 plus the voltage in R3. Okay, so the sum of all the voltages passing through here should equal to 0. For your Kirchhoff's loop rule, it follows the conservation of energy. So it says that energy can neither be created nor destroyed. That's why the energy that is coming from your potential difference should be the same energy that is divided all throughout in your circuit. So you gain potential energy going through the battery or your EMF, and you lose potential energy going across resistors in the direction of positive current where your voltage drops. Okay. If you end up where you start in a circuit, you have to be back at the same potential. So that is the change in your potential should equal to zero. That is according to the conservation of energy. These are the sign convention for the loop rule. So first you have the sign convention for your EMFs. So in your loop rule, you have seen earlier that we actually draw your travel line. Okay, and let's just call that one as your travel or the way you pass through your components. And you have a positive EMF if you travel the direction from the negative to the positive. So it's positive if you travel from negative to positive. So in your equation later, if you travel this way, you have an EMF that is positive. And your EMF is negative if the travel direction is from positive to negative. So if you travel from the opposite end, okay, from positive to negative, you have a negative EMF in your equation. And you gain potential energy as you move in the direction of your EMFs. Just remember this one. You gain potential energy as you move in the direction of your electromotive force. And you lose potential as you move in direction of a current across a resistor. So this is the sign convention for resistors. Remember your Ohm's law. So from your Ohm's law, you have V equals IR. And you are going to use this one as you travel across your resistors. And remember that there are current directions in your circuit. Okay. Sometimes you are given with the current direction. Sometimes also you um, you imagine your currents passing through your resistor, and then you give the direction of your current passing in your in your loop. This is the sign convention for your resistors. You have positive IR if you travel opposite to the current direction. For example, here the current direction is to the left, and then you travel according to the way you travel in your loop. It is in the opposite direction as your current direction. Then this is a positive one. Okay, so just remember, uh, if you move opposite to your current, so this is your travel. So you have a positive voltage or positive IR. And you have negative IR if you travel in the current direction. So if your current and your travel direction are in the same direction, you have a negative IR or a negative voltage. And you lose potential as you move in the direction of current across the resistor. So let us have an example. Okay, remember your just remember your junction rule, and then remember also your loop rule. So we have here a circuit. Okay, so use Kirchhoff's rules to determine the current in your 1.2 ohm, which is at the top, and then your 15 ohms resistor in the middle, and then your 1.2 ohm resistor in the bottom, as shown in the circuit. So we're asked for the current here, the current in your 15 ohms, and the current in your 1.2 ohms, or our target are, so our targets are I1, I2, and I3. And the first thing that we usually do is to find for um, a junction where you're going to apply your junction rule. So according to or from Kirchhoff's junction rule, so we're going to use this acronym here, your KJR, Kirchhoff's junction rule. Okay, let's find for a junction where we're going to find the sum of all your currents. And I'd like to have this junction here. Okay, so take note of this junction here. You can also choose the other junction, which is this one. Okay, the right end. But I just like the junction in the red or the junction in the left side of your network. So you have three currents here. As you can see, you have your I1, your I2, and then your I3. Again, any current that goes into your junction is positive, and anything that goes out of your junction is negative. And as you can see, your current I1 goes into, your current I2 goes out of the junction, and then your current I3 goes out of the junction. So from your Kirchhoff's junction rule, you have this one here. You have the current I1 that's equal to I2 plus I3. And we label this one as your equation 1. So what we just have here is that you have your I1 minus I2 because it goes out, minus I3 again because it goes out, and that's equal to 0. And we rewrite it in terms of this equation here. And then next we're going to apply for your Kirchhoff's loop rule. So the first thing that we do is to draw loops, and your loop direction will be your travel direction. So you can draw your loops like counterclockwise, or you can also draw your loops clockwise. Okay, it depends on you. Again, you can draw your loops clockwise or counterclockwise. It depends on your decision. Your loop direction will also be your travel direction. So let's draw loops here. So we have, let's say, this loop. Let's refer to one as your loop 1. And then I just like it that my next loop is this one here, your loop 2. Of course, you can also use the larger loop, which is this one here. Let me just draw it. Draw some lines here. So this is another loop. You can also use that one, and you can label it as I3 or loop 3. And you can just draw it just like this. So you have your loop 3 outside. Okay, so you have 3 loops. But here, we have 3 unknowns, I1, I2, and I3. And according to algebra, if you have 3 unknowns, you need 3 equations to solve for your 3 unknowns. If you have 4 unknowns, you need 4 equations. If you have 5 unknowns, you need 5 equations, so on and so forth. Since we only have here 3 unknowns, so we only need 3 equations, and I already have equation 1. So I need just 2 more equations, and I'm going to get this equation from your loop 1 and loop 2. Okay, and from Kirchhoff's loop rule, you have your loop 1. So your loop 1, okay, let's start traveling from your 9 volts. Okay, let's start traveling here. Start here. If we start here, and then our travel follows again the direction of your loop that you draw. So we have a counterclockwise. So our travel here, this is positive, so you have 9 volts. So we go around your loop, and then we pass here. So the current direction is this way, and your travel is this way. So they are in the same direction. So you have minus 15 ohms times I2. So this is your V equals IR. Okay, remember this is your IR. V equals IR, which is equal to your voltage. Okay, so, and we continue with our travel. So we move here, passing your 22 ohms. And your current in your 22 ohms is going to the left, and you're also going to the left. So that means you move in the same direction. So since that is in the same direction, you have a negative 22 ohms. And you pass another resistor, which is your 1.2 ohms. Your current is still to the left, and then your direction is still to the left. So that means you have negative 1.2 ohms. And you can sum these two. These are just 2 resistors in series, which is equal to negative 23.2 ohms times your current IY or I1 passing through your 1.2 and then your 22 ohms. That's equal to negative 23.2 I1. So this is labeled as equation 2. Okay, so just always remember that when you're going to travel in the opposite direction as your current, you have a positive voltage. If you travel in the same direction, you have a negative voltage. So that is all for your loop 1. Now let's go to your loop 2. For your loop 2, I still chose to travel counterclockwise, and let's start here at your 6 volts. Okay, so if we start traveling there, you have 6 volts. You have positive 6 volts, and then positive 6 volts, we go around, we pass this 15 ohms. So this is our direction. Our current for your 15 ohms is going to the right. You are going to the left. So that means you have uh, you have 15 I2, which is positive since your current and then your travel is in opposite directions. And then you move past this one, and then you continue your travel, and then you pass your 1.2 ohms resistor. And here you travel in the same direction as your current. So you have a negative 1.2 ohms I3. So your equation 3 is just 15 I2 minus 1.2 I3 plus 6 volts, and that is equal to 0. And these are already 3 equations, which means that we can already solve your 3 unknowns. You can still write for your loop 3, but as you see, your loop 3 is actually just a combination of your the equations in your loop 1 and your loop 2. So we're not going to deal with it anymore. These are again your 3 equations. We've labeled this one as your equation 1, equation 2, and equation 3. And in order to solve for your I1, I2, and I3, you just do some algebra. So this is just your algebra. And then you just need to eliminate terms in order to solve for I1, I2, and I3. And this is how I do it. So it depends on you. So there's no specific solution. You can do it in any way that you like. Just use your algebra. So from equations 1 and 2, so I have first equation 2, and then I inserted your I1, which is equal to I2 plus I3 into this one here. Okay. So from equations 1 and 2, I have 9 volts minus 15 I2 minus 23.2 times your I1, which I replaced with I2 plus I3. So I substituted I1 into the I1 in equation 2. And so again, I have this one here, and I can simplify it. So simplifying it, you have 9 volts minus 38.2 I2 minus 23.2 I3. That's equal to 0. And we can anymore simplify this one further. Okay, so I just label this one as equation 4. And from equation 3, I just rewrote, or I just rewritten your equation 3 in another form, such that I take out your I3. And from equation 3, your I3 is equal to 12.5 I2 plus 5 volts. So you can try it yourselves. I just rewritten your equation 3 in such a way that I took out your I3 out of the equation. And from equations 3 and 4, so I will be using now your equations 3 and 4. This is again your equation 4. And take note that from your equation 4, I have a term of I3. And I will be using this I3 to substitute it in this equation here. Okay, so I'll be substituting that I3 in the equation, such that you have 9 volts minus 38.2 I2 minus 23.2 times your I3, which is 12.5 I2 plus 5 volts, and that's equal to 0. Simplifying further, you have this equation, and adding like terms, you have negative 107 volts minus 328.2 I2, that's equal to 0. And as you can see, I can already solve for I2 by dividing 107. Okay, let's just rewrite it for you to see. So I have 32 328.2 I2. That's equal to negative 107 volts. Divide both sides by 328.2. Then you are left with I1. And by the way, this is in ohms. Okay. So your I1 is equal to, or sorry, your I2, I mean, so this is I2, I'm sorry. So your I2, I mean, is equal to negative 0.326 amperes. So it's equal to negative 0.326 amperes. Back again, you have I2 that's equal to negative 0.326 amperes, and we're going to solve this one to find for I2 and I3. From equation 2, this is your equation 2, 9 volts minus 15 I2 minus 23.2 I1. We substitute the value of your I2 in the equation, and we get this one. We have 9 volts minus 15 times negative 0.326 amperes minus 23.2 I1. And adding like terms and solving for I1, we get an I1 that's equal to 0.599 amperes. From equation 3, we can solve for I3. So equation 3, you have 15 I2 minus 1.2 I3 plus 6 volts. Substituting I2 into equation 3, you have 15 times negative 0.326 amperes minus 1.2 I3 plus 6 volts. You can solve for I3 that's equal to 0.925 amperes. And you can verify your answers using equation 1. That is, your 0.599 amperes should equal to I2 negative 0.326 amperes plus 0.925 amperes. This two should be equal in order to say that you got the right answers. Otherwise, if it's not, then probably there were some mistakes along the way. So you need to review again your answer if you did not if you can verify your values. What's a negative current? Okay, this negative current that we see here, we have solved negative I2, and that just means that the direction of I2 should be in the opposite side. So this is, or I2 should be going that way in order to get a positive I2. So you should have I1 going in, I2 going in, and then I1 plus I2, it goes as I3. So that is what your negative I2 represents. So that's it. That's your I1, I2, and I3. So let's have another example. We are given with this network here, and we're asked to use Kirchhoff's rule to determine the current of the circuit. You have currents I1, I2, and I3, which are our target. So the first thing that we need to do is to find a junction. We can use this junction here, or we can also use this junction here. So whatever the chosen junction that you use in your solution, it doesn't matter because you will end up with the same equation. Okay, and let's just say that I'd like to use the junction at the top. You have I3 that's going into your junction, I2 that's going into your junction, and I1 that's going outside of your junction. So if that is the case, you have I2 plus I3, that's equal to I1. From your Kirchhoff's junction rule, you have I1 is equal to I2 plus I3, and I label this one as equation 1. From your Kirchhoff's loop rule, we find loops. And as you can see, we have 3 unknowns, so we just need 2 more equations. So let's just look for 2 loops. And I just like to travel again in the counterclockwise direction because I'd like to travel from the negative to the positive polarity of your power supply or your potential difference. So let me travel again counterclockwise. Okay, so we have two loops, and let's say that this is your loop 1 and then this is your loop 2. So from loop 1, so I travel from your 6 volts, so you have positive because I travel from negative to positive. So you have positive 6 volts, and you have here your current I1. So I travel in the same direction as the current in your 12 ohms. So um, you have negative 12 ohms. So you still have I1 here. So you still have I1 passing through your 8 ohms. So you have you travel, or our travel is still in the same direction as the current I1 in your 8 ohms. So you have minus 8 ohms. And as you can see, these two resistors, your 12 ohms and then your 8 ohms are just in series. So we can have negative 20 I1 voltage for these two resistors here. And after passing through your 12 ohms and 6 and your 8 ohms, we travel past your 6 ohms, which is here. Our travel is still in the same direction as your current I2, so you have negative 6 I2 voltage passing through your 6 ohms. And you have this equation here. You have 6 volts. I have 6 volts minus 20 I1 minus 6 I2, that's equal to 0, and I label this one as your equation 2. Next, we travel in loop 2. So for loop 2, I start with 3 volts. So I travel counterclockwise. So that means I travel from the negative to the positive terminal. So you have positive 3 volts passing through 2 ohms. You have the same direction. Your travel is in the same direction as your current I3. So you have negative 2 ohms I3, and then you pass your 6 ohms. This time, the direction of the current is in the opposite side as your travel. So you have positive 6 I2, and then you pass through your 10 ohms, where in your 10 ohms, your current I3 is still the same current passing here because this is a series network. So you have negative 10 ohms. So since these are just in series, so you have 2 ohms plus 10 ohms, so you have 12 ohms. So our equation for loop 2 is you have your 3 volts minus 12 I3 plus 6 I2, and that's equal to 0. And now we have 3 equations, and we can now solve for your 3 unknowns. So these are again your 3 equations, which we have uh, written in the previous slide. So you have your equation 1, equation 2, and equation 3. And again, to solve for these equations, to solve for I1, I2, and I3, we still use the same method, which is we are still going to use your algebra. Okay, so it depends on you and how you're going to solve this problem here, but it's just your algebra. So we start solving from equation 1 and equation 2. This is your equation 2. And from equation 1, I can replace your I1 with I2 plus I3. So you have this one. You have 6 volts minus 20 I2 plus I3 minus 6 I2 is equal to 0. And simplifying the equation, you have 6 volts minus 20 I3 minus 26 I2 that's equal to 0. And I label this one as your equation 4. From equation 3, I just have rewritten your equation 3. Okay, since I've not used equation 3 yet, so I'm going to rewrite your equation 3, taking out I2 of the equation. So you have I2 that's equal to 2I3 minus 0.5 volts. So this is just equation 3 rewritten in such a way that your I2 is taken out of the equation. And from equations 3 and 4, this is your equation 4. I'm going to replace I2 here with 2I3 minus 0.5 volts. So you have 6 volts minus 20I3 minus 26 times 2I3 minus 0.5 volts equal to 0. And simplifying, you have 6 volts minus 20I3 minus 52I3 plus 13 volts. And adding like terms, okay, you have 19 volts minus 72I3. And we can solve now for I3. I3 is equal to 0.26 amperes. Again, you have I3 that's equal to 0.26 amperes, and we're going to use this value to solve for I1 and I2. From equation 3, we can use I3 value of 0.26 to solve for I2. Okay. So you have your I3 or equation 3 that's equal to 3 volts minus 12I3 plus 6I2 that's equal to 0. I'm going to replace I3 with 0.26. And solving for I2, you have 0.028 amperes. From equation 2, I can use the value of I2 to solve for I1. So you have I1 is equal to 6 volts minus 20, or you have equation 2 that's equal to 6 volts minus 20 I1 minus 6 I2. Using 0.028 amperes in your I2, we can solve for I1. And your I1 is equal to 0.29 amperes. And you can verify your answers using equation 1. That is, your 0.26 plus your 0.028 should equal to 0.29 amperes. If that is equal, your I1 is equal to I2 plus I3, then the values for your current are correct. So let's end this video with an assignment. So you have this network here of 5 resistors. And in your network, you have 2 power supplies or your 2 source of your EMF. And for your assignment, you are going to find for the currents that are passing in each of the resistors. Okay, for your assignment, you're going to find for the currents passing through each resistors. That is, your target is you're asked to solve for the current here, current also here, current on your 1 ohm, current in your 3 ohms, and then the current in your 1 ohm resistor. And as you can see, there is no current direction given. So in this example, you can actually you can have your own directions of your currents. Anyways, if you are getting a negative answer, then that means that your current direction is different from what should be the direction of your current. And uh, just to start, okay, so we have 2 junctions here, this junction here, and then another junction here. So in here, the currents passing around this line here is the same. Also for around here, that should be the same, and for this one here. So as you can see, we have 3 currents, and just for example, I have these 3 currents here. This is just for example, so I just have this one. So I assume that I1 is going into the junction. Okay, again, I assume that I1 is going into the junction, and it goes out as I2 and I3. But of course, you can have it in a different way. Okay, you can assume it like your I3 is going inside, your I1 is going inside, and then your I2 is going outside. Okay, so again, I just assume this current directions, and it depends to you on how you want the current to go in. But if ever if you got a negative current, then that means that the current for that specific conductor should be flowing in the opposite direction. And for your assignment, please follow these current directions, okay, and solve for the currents in each resistor. So good luck and thank you for listening.